Okay, so what we're going to do today is finish up fields, the fields topic, by going over escape velocity and orbits. Mostly, I think, just a way to find orbital velocity, but orbits and escape velocity. So uh, that's our plan here for today. So we'll start with escape velocity. Now, for this, we can solve basically with energy considerations, but what we need to realize is what we're trying to do is we're trying to go from our planet, we'll call it a big mass M, and we're trying to shoot something off with an initial velocity so fast that it escapes out to infinity, way all the way over here at infinity, and it never comes and falls back down, essentially. That's what we're trying to do. Now, this is different than launching a rocket into space because the rocket is constantly powered, whereas this is just an initial velocity we're giving it, and we're not continuously burning rocket fuel and pushing on it on the whole way up. So it's a little different than that, but it gives you an idea how fast you have to move to if you had to just jump, how fast would you have to jump in order to get off the planet out to infinity. And we're going to do this by energy considerations. Over here, uh, we're basically going to have kinetic energy and potential energy. So kinetic energy and potential energy. And over here, we're going to get to the point where when our velocity goes to zero and we have no kinetic energy left, all we have is just potential energy. Final, and we'll call this initial and initial. And we're going to do conservation of energy. We're going to set these two things equal to each other and go ahead and solve them. Now, the way this is done is out here, this potential energy is set at 0. Remember, you can pick any 0 point you want for potential energy. And what's typically done is you choose this as 0 all the way out here, because at this point, you're so far away, you're infinitely far away, that if you're not moving and you're there, you're so far away that this can't actually pull you to it because you're out at infinity. And at that point, that 1 over r becomes 0, and you don't have any potential anymore. So that's our 0 point. Now, as you fall closer to the planet, if you did start to move, say you gave yourself a little nudge, so you weren't quite at infinity, you were at like infinity minus 1 meter or something, where you could actually then be pulled in, uh, your potential energy would decrease and it would become more and more negative. And as it became more and more negative, you would gain kinetic energy. And the idea behind this potential energy being thought of this way, and that all these potential energies for things that aren't at infinity then are negative numbers that become more and more negative, is that that's basically the source of energy for the whole universe of kinetic energy and mass, because if you added up all the negative potential energies and all the positive kinetic energies and all the mass due to the potentials positions in the fields like that and stuff here, you add this all the energy up in the whole universe, then you would basically get 0. And so energy is conserved even for the entire universe essentially being 0. But we're going to use it here just to kind of calculate this. So for the initial part, we have 1/2 mv squared, and that's our initial velocity. And then we're going to use our potential. Remember we had in that last video we had Vg equals the work done moving something, which is our change in potential energy per mass. So what we can do is basically put here that we have to add on our Vg times m, and then that has to all equal 0, that potential energy at the end. Now remember, this Vg, this potential, we could calculate with negative g and then big M, our big capital M, over r, and then of course if we multiply in our little actual mass we're trying to get rid of onto it, and we'll have our 1/2 mv squared still here, mv initial squared. And so if we do this and it equals 0, we can then subtract this over to the other side, which ultimately ends up then adding a negative. So you end up with 1/2 mv initial squared is equal to g little m big M over r. And now these little m's are the same, so we can actually go ahead and cancel them out. We can divide both sides by little m, and it will be gone. And then we need to just isolate this v initial, which will be our escape velocity. So maybe we should change the name to VE at this point. V escape is going to equal 2g big M, the mass of your planet, over R, and then all of that square rooted. And that would be our escape velocity, 2gm over R. So that right there gives you basically what you'd have to do to get this. And I believe if you calculate this out for Earth, the escape velocity of Earth, I think it's around 11 point something, 11-ish kilometers per second. So it's actually really, really fast. 11 kilometers per second is not very slow. That's faster than the speed of sound. Not faster than the speed of light, but faster than the speed of sound. So that's actually a really fast speed. In order to escape this planet, you'd have to jump really, really fast. So that's the idea behind escape velocity that allows us just to go woo, we make it all the way out here to infinity and never fall back down. Be very hard to match that speed here on Earth. I'm not sure what it is for the moon, but I'm sure it's less than that. So next, we'll talk a little bit about orbits and figure out, what's the speed of something in orbit. And we can do that pretty simple because if we assume something is in a circular orbit, then say here's our planet, mass m. Sorry if that's maybe a little small. I could probably make that a little bigger here. So let's do our planet again, mass m, in the middle of our planet, and then we'll have our small little object out here going in a nice circular, like my perfectly drawn circle there, a nice circular orbit where the radius stays the same the whole time. And at this point, this becomes a centripetal force problem. And we can say that if we go to work out all the forces on this, we have gravity pulling down. We can then set that equal to our centripetal force, and we can have that centripetal force is equal to our gravitational force in this part, just like what we had before when we'd have tension in lines and we would work it all out. And the center-seeking force then is going to equal that gravitational force pulling on it. If we can then do that, remember centripetal force is m, the mass of our little object, that's our little m, mv squared, which will be our orbital speed, mv squared over r, which is our distance out here, that's r. And then the gravitational force is g, then the little m, the big M, the mass of our planet, our central object, over, and in this case, our distance away from the center. Actually, this really should have been drawn coming from the center, not from the surface of the planet, over r squared. From here, you can go through, you can solve this for v, you can cancel out, multiply both sides by r, get rid of one of the r's, you can divide both sides by the m, so the mass of the actual orbiting object doesn't matter, in which case you take the square root, and you end up with a value of the orbital value, orbit, for the speed is simply square root of g mass of your central object over r. And so it's very similar in form to this, but not quite as big. This has this square root of 2 coefficient out in front that this one is missing. It's just gm over r, whereas this was square root of 2 gm over r versus square root of gm over r. And so that will essentially do that for us. Okay, I think that's pretty much it for what I wanted to cover for escape velocity and orbits. I guess that's it.